Hello, everybody, and welcome to Technically Speaking, Episode 3, Balancing the Drying System. I'm excited to bring this topic to you today. It's going to be a great summary of some of the information that we've covered so far. My name is Brandon Burton. I am the Vice President of Technical Application here at NextGear and CoreLogic, and I'm also the Chair of the ANSI IICRC Standards. I'll be talking to you today about the subject of balancing the drying system in a water mitigation environment, using a lot of the information that I've gleaned from participation in standards over the course of the last couple of decades. So this is a subject that's near and dear to my heart because I think it's a critical component of effectively drying buildings. So we're going to bring a lot of technical speak into today's conversation, but we're also going to do a bit of review of some of the information that we've covered so far. A couple housekeeping notes before we get started. First of all, do note that the chat is turned off in Zoom as we go through the presentation, but the Q&A is open. So please, if you could, take a moment just to find that Q&A area inside of Zoom if you're not familiar with it. And make sure that you have that ready, because at any point during the presentation, if you'd like to drop a question in there, we'll log those questions. And at the end of today's presentation, as we typically do, I'll go through a Q&A session with all of the attendees. So what I found in a lot of the feedback on these technically speaking presentations is that a lot of people get a tremendous amount of value out of that Q&A session, and no questions off limits. So feel free to post any question you'd like, and I will do my very best to make sure that we address those questions. So with that said, let's go ahead and roll into it and talk about technically speaking and get into balancing the drying system. So first of all, to kind of get us rolling here, let me give you a bit of an overview of where we're going to go in the presentation today. Obviously, the main topic today is balancing the drying system. But as a part of that, the first thing that I want to do is review some of the concepts that we discussed in episode 1 and episode 2, and add a little more color to them as we go. It's important that as we get into this topic, that some of those basic things are understood. We're then going to go into a concept that I call balancing for both space and time. All right, which sounds a lot different than it actually is. But balancing a drying system really requires you to look at the project in two different perspectives. Balancing the space for drying and then balancing the system over time, because the job changes, right? One of the things that makes water damage so unique, the mitigation process so unique, is that what we're handling for a project on day 1 is drastically different than what we're handling on day 2 and then day 3 and day 4. In fact, I'd make the argument that if you're dealing with the same exact project on day 2, you're doing something wrong, right? The environment needs to be changing. And because the environment is changing, our approach must change with it, right? How we're attacking that project must also change. So balancing is not just about a one-time exercise. Balancing is something that we're going to revisit each time we monitor that project. So we'll talk about it from both of those perspectives. That's going to rely on understanding how to measure that environment for the impact that we're trying to achieve, and then making adjustments, the appropriate adjustments based on what those measurements tell us. So we'll get real deep into understanding a couple of the most critical measurements when it comes to balancing the drying system. So with all that said as an overview, let's jump right into it and get into some of our review concepts from episode 1 and 2. So most of you hopefully were with us for episodes 1 and 2, and you'll remember that one of the things we discussed in episode 2 was this concept of HAT, right? And this probably draws on your WRT certifications, your very first training exercises that you probably went through in this industry, where we learned that HAT was a simple concept that helped us understand the properties of air that control, influence, or regulate the way we dry a building. And simply expressed, HAT stands for humidity, airflow, and temperature, right? And we've kind of drilled into this concept more deeply to understand that balancing a drying system and achieving drying means that all 3 of these entities have to be controlled. Some examples of this would be that you can have a really good low humidity in a drying environment and a really good warm drying temperature, right? So a low humidity, just to throw some random numbers out there, you could be at a 20% relative humidity, or all the way down around 30 grains per pound. And you could have a warm drying temperature up around 75 to 85 degrees Fahrenheit. But if we don't have airflow on the wet surfaces, then that environment is actually perfectly conducive to mold growth, because mold occurs with the humidity at the surface, right? And without air movement, that low humidity that we observe 3-4 feet above the floor is irrelevant, right? That humidity is not the humidity that is preventing damage, that is causing drying to occur. It is the humidity that is in contact with or in concert with the building materials that's doing the work. And that's part of the concept of HAT, is understanding not only that all three of these are important, but where they're important and how we measure for it. So as we get into balancing the drying system, one of the concepts that's really important to hold on to, that is one of the industry's best kept secrets, is that your psychrometry isn't a hygrometer held out at chest level, right? That psychrometry is important, but it's not the psychrometry that's doing the work. The psychrometry that's doing the work is the air in contact with the wet surface. And if there's one thing that I've really tried to drive home in these first few episodes of Technically Speaking, is just how important that is. And if that's the only impact that this entire series has on your activities in the field, then we've made huge strides as an industry to make sure we're understanding what's happening at the surface in communication with the wet material. So that was one concept in episode 1 and 2 that we covered. Another one that I want to dig into here a bit more deeply is understanding how the project changes over time. So it's not just HAT today, humidity, airflow, and temperature today. It's what do I need right now based on the amount of moisture that's present right now and what's affected right now. Then when I come back 24 hours later, what's changed, right? Hopefully a lot has changed, but based on what has changed, now what do I need? What's the balance that's appropriate at this point or this juncture in the project based on where the water is, how much is present, and what affected materials still remain? If that has changed, then just think about it logically for a moment. Wouldn't also then the drying system change, right? The resources I'm using, how they're allocated, where they're placed, what I'm trying to focus on, all of that should be different because the project is different. And I think if we all honestly step back for a moment and think about some of our mitigation projects, how often do we place equipment on day one and then come back 24 hours later, it's making progress, so we don't change anything, right? It's working, so why change anything? Which is a really broken mentality. If the project is now different, then you probably would have set it up differently if that's where you started. And that's probably one of the best ways to approach this as I get into this topic, is each time you revisit the project and do a monitoring visit, try to kind of trick your brain a bit and say, if I were setting up brand new today, forget about what was there the previous 24 hours. If I was setting up brand new today, and this was my starting point, how would I set up the project? Right? What would I use? What resources? How would they be focused? How would they be allocated? Where would I designate my airflow? Where do I need energy? Where do I need temperature? Right? The benefit of the last 24 hours of drying will help you understand whether or not your resources are controlling the environment, which we'll talk about. But you need to think about that project as being a new project, at least to a degree, to help you drive making those adjustments. So balancing for time, let's talk a little bit about what I mean about this. So let's take a look at a project. And on a little graph here on this far left-hand axis, we're going to talk about the amount of moisture that is in the air, right? And then along the lower axis, we're going to look at time and how time changes or progresses through the project. We're going to put on here an initial reading of the air that's in this environment and just talk about humidity for a moment, right? And this is an analysis we'll use for more than just humidity, but let's just talk about humidity for a moment and the measurement of that humidity in grains per pound, right? The actual amount of water vapor in the air, not relative humidity, but in grains. And let's pretend for a moment that we've taken this reading at this particular point in time and we've got 41 grains per pound. And then a certain amount of time transpires. This could be a day, this could be hours. Let's not worry about that for a moment. And let's say that that second reading, after a period of time has transpired, now indicates a higher grains per pound, right? So this should bring out some really obvious red flags, all right? Hopefully it does, that I've taken a reading and then a certain amount of time transpires and humidity is now increasing over time, right? The amount of moisture in the air is now greater. This is problematic. Unless it's intentional, it's problematic because this indicates that there is not an appropriate balance in my drying environment, at least not over time. There's not an appropriate balance. And what do we mean by that? We mean that there is a rate of evaporation that is occurring within the environment. And that rate of evaporation is not being matched by an appropriate amount of humidity control, right? That may be dehumidification or ventilation. Let's just call it humidity control. This balance is off. Now, this is kind of the obvious part of balance and time. Let's talk about the not so obvious parts. Typically, the reaction that many have when they see this problem is that I must not have enough dehumidification, right? My dehumidification must be inadequate. So the knee-jerk reaction is, let's add more dehumidifiers, right? Humidity is increasing over time. Let's throw more dehumidifiers at the problem. And now we see the humidity begin to decrease over time. And then we kind of check off on our mind that we've solved the problem. In reality, however, we haven't. And this is the second really big industry secret I want to talk about today, is very often we're driven to satisfy symptoms without truly digging in and understanding the problems that are causing that symptom. And let me give you some examples of what I mean by that. And again, this is a review of a concept we discussed in episode 1. What if the reason that humidity is increasing over time is because we're having problems with our electrical distribution, right? Let's say that the dehumidifier has been tripping breakers and the homeowner's been turning it back on for you or whatever else. It hasn't been running consistently. Adding more dehumidifiers isn't going to fix that problem. It's going to exacerbate that problem, right? It's going to make it worse, right? How would I know if that's the problem? I would know if that's the problem by tracking my hour meters, right? I should see an additional 24 hours on that meter if I'm checking every 24 hours, for example, right? So let's say that that's not the problem. Let's say that the problem is that we have additional moisture in the environment that hasn't been addressed. Let's say there's a water source that has not been identified, and there is still bulk water in that environment. And the reason humidity is increasing over time is because I'm not properly compensating for that bulk water. It wasn't extracted, that source wasn't identified, et cetera. If I throw additional dehumidifiers at the problem, I'm just going to mask that issue, right? I'm curing the symptom, I'm not curing the problem, right? Let's say that's not the issue. Maybe the issue is just the performance of the dehumidifier in and of itself. Let's say the dehumidifier is a 20-year-old machine that is in severe need of maintenance and hasn't had a filter changed over that 20-year period, and it's just not giving me the water removal that I expected from it. Adding dehumidification is not an appropriate fix there, right? It should be swapping out the dehumidifier. The reason I'm going through all of these scenarios is a couple of fold. First of all, when I identify that my system is not achieving the balance that I expected, the concept we talked about in episode 1 was asking the question why, at least 5 times. Why is humidity not in balance? All right, because evaporation is happening faster than dehumidification. Why is dehumidification not keeping up? Keep asking that question until you get to the base of the problem. Then once we get to the base of the problem, we can make the appropriate adjustment to address the balance, right? And again, the reason I urge this is because this is, again, it's another kind of reactionary thing that we do as an industry, is when we identify a symptom like this, we very often apply a solution to the symptom and not necessarily the problem. It is critical to identify the core problem before we apply that solution. So that's the second concept I want to quickly review as we get into today's material. Now let's talk a little bit about balancing for space. Okay, so that was over time and watching our humidity over time. Let me introduce the concept of balancing for space. The purpose of air movement in a drying environment is really twofold. There's 2 primary reasons why we have air movement. The reason for air movement is to provide circulation throughout the space, right? To ensure that air at one area of the space is representative or similar to air in another area of the space, as long as we're talking about inside of our drying chamber. The second reason air movement is there is to create velocity across the wet surface. All right. Ideally, that velocity at the wet surface is going to kind of do the same thing as the first concept we talked about. It's going to provide a circulation vertically. It's going to remove the wet, moist air from the surface and replace it with the drier air from up above. If that's the purpose of air movement, and if that's important to our overall purpose for drying a building, it's something that we need to check and monitor and ensure is being done properly. So here are the 2 different concepts that we just discussed. On the left-hand side, we see that vertical circulation where we have velocity across the wet surface. On the right-hand side, we see that circulation from one space to the next. It is absolutely critical that we verify that the air movement is achieving both of these forms of circulation. And it's very simple to do. For example, if I pull out a hygrometer and measure both the air at 3 or 4 feet above the surface, and then measure again the air near the wet surface, I should find that these readings are practically similar. Okay. In other words, I'm not concerned about a 1/10 of a degree difference or a 1/10 of a percent relative humidity difference. But if the air above my surface, well above my surface, is at 30% relative humidity, but the air in contact with that wet floor is at 70 or 80% relative humidity, that's a problem. The air movement has not been effectively deployed. Let's take a step back and understand why that's important. Again, the air that is 3 feet above or away from that floor is not the air that's drying the surface. The air that is doing the work is the air that is in communication, in direct contact with that surface. This environment, if these are drastically different, is going to dry very, very slow. We're going to have very slow drying rates and a high likelihood of secondary damages that will occur to that surface. So it's critical we address it. The same when we're talking about the space circulation from area to area. If this drawing on the right-hand side were a drying chamber that had these 3 separate spaces, again, it's important that I measure the temperature and humidity in one end of that space and then verify at the opposite end of that space, that furthest walking distance between one area and the next, that those readings are, again, practically the same. Again, not worried about 1/10 of a degree or 1/10 of a percent, but if we're off by 10 or 20% or 5 or 6 degrees, that's significant. And it's going to have a significant impact at the rate of drying. For example, on the right-hand side, if we had 80 degrees at 20% relative humidity, a good drying condition, but at the opposite end, we have 60 degrees at 70% relative humidity, obviously there's going to be a drastic difference in the rate of drying. Air movement is the solution to that deficit. Air movement is what's lacking in the circulation between these 2 spaces. And again, I'll back up to the initial statement. Air movement's purpose is to create that circulation. So again, here, kind of the little industry secret is that many of us will grab that hygrometer that measures temperature and relative humidity, and we'll take the measurement in what we call the affected area, right? We'll walk into a drying chamber, right? That space that we're drying in, and we'll take a reading in that chamber and we'll log that reading. And we'll make the assumption that that reading represents all of the air throughout that drying chamber. And we can't make that assumption, right? This is the primary reason why you'll have areas that'll dry very rapidly in parts of a project, but then you'll have another area on the project that takes an additional 2 or 3 days to dry. Sometimes it's just because of the density of the material and how complex the assembly is, but many times it's because we haven't verified that we have appropriate circulation. And I'll share another really important secret with you. It doesn't matter if part of the job dries in 2 or 3 days and another part of the job dries in 5 to 7 days, right? The job took 7 days if that's the longest it took for the wettest point to achieve a drying goal or dry standard, right? So we have to create the circulation so that we get the appropriate balance within that drying environment, okay? So a few different concepts here that I wanted to review. The last one I want to hit here on review is going to be something we call hat plus time, all right? This is an important one because it drives home that initial statement that I started with. Humidity, airflow, and temperature are the properties in air that we control or manipulate to facilitate drying. But that balance changes over time, right? As the job progresses and what amount of water we're chasing, where the water is, as that begins to change, so should the balance of hat. And this model really helps draw out what those changes look like, at least in principle, what those changes look like. So balancing hat over time. So throughout the drying project, the elements of hat vary in priority. This occurs because water exists in 3 different states. The first state of water that we address is something called surface water. And surface water is readily available in a liquid form right at the surface. It's the water that, if we were to put our hand in contact with the surface, our hand would actually become damp, right? That's surface water. Typically, you can see it, not always if it's a really thin film, but typically you can see it sitting right there at the surface. Air movement is in direct contact with that surface water. And because air movement is in direct contact, notice here on this model how air movement fills the majority of my focus, the majority of my priority. Humidity up at the top, temperature down at the bottom. We need to control them because we need to prevent damages elsewhere, but I don't need a 20% relative humidity to get surface water to readily evaporate. I just need good, rapid airflow right at the surface, right? Now, as surface water dissipates, the priority begins to shift a little bit. We move into a region that we call free water. and something that in technical speak we call the falling drying rate. When we start to get into free water, we're still dealing with liquid water, but that liquid water now exists in the pockets and voids inside of the material, not necessarily at the surface. It's still liquid water, so its evaporation is still relatively high. It still makes relatively high humidities near the surface, so we still need an ample amount of airflow. But what becomes more important is lowering the humidity in contact with the material, and if that's not enough, raising the temperature of the material. And again, I stress of the material. What dries best in a drying environment is not warm air, it's warm materials. In fact, the most ideal drying environment, the air is not going to be all that warm at all because dehumidification performs best when the air is not hot. It's the material that will be warm, right? That's what needs to be warm. Typically, we use warm air to warm the material, and that's why we end up with warm drying environments. But if you could create a warm material without making the air too awful warm, you would have an ideal situation for drying. As we move past free water, we get into the hard falling rate of drying. And the final stage of that drying process is something we call bound, right? Bound water it's really a different state of water altogether. It's no longer a liquid form. It's not a vapor form. It's not a solid form. It's water that has become chemically bound or physically held by the structure of the material itself at a molecular state, at a molecular level. And that bond requires energy to break. In order to release that water from the material, there has to be ample energy associated with that water to break free of that bond. When we hit the bound state, notice how the importance of air movement almost becomes zero as we hit the final stage of drying. But what becomes absolutely critical is a low humidity and a warmer temperature. So the emphasis at this stage is what we call a low vapor pressure of air, low humidities in the air, and a high vapor pressure with the material, a warm material. And the more we can focus or emphasize low humidity and warm materials, the more rapidly we'll remove bound water. So this is how the priority shifts and changes over time in principle, okay? Hold on to that because we're gonna need to draw on that information again here in just a moment, okay? So with all the review complete, now I want to dive a little bit deeper into the concepts that I'm setting us up for today. How do we measure for balance? What does that measurement look like? So in episode 2, we talked a little bit about the use of hygrometers on the surface of materials. And there are 2 different types of hygrometer measurements that you may take near a surface. I want to be really, really clear on the difference between these 2. In one measurement, we're simply placing the hygrometer near the surface. Okay, just near the surface. No other special measures are being taken. No plastic is being used. We're not covering anything. We're just placing the hygrometer near the surface. And what we're trying to measure is we're measuring the humidity at the surface during the active drying process. So whatever air movement you've got running, it's still blowing by the hygrometer. Your dehumidifiers are still doing their work. You're just placing that hygrometer near the surface and measuring the amount of moisture in the air and the temperature of that air that is near the surface. You're then going to compare that reading to the standard reading that you normally take, right? You standing in the middle of the room and holding out your hygrometer and measuring what's going on about 3 feet above the floor, right? Or 4 feet above the floor, depending on how tall you are, right? So you're measuring that air and making a comparison between these 2. This comparison between the 2 helps you understand the space balance. How well have you installed air movement to put your dry air in contact with the wet drying surface, all right? Now, this is the simplest version of this. When we're dealing with more complex assemblies with multiple layers and air gaps and interstitial cavities, that hygrometer you see on bottom should actually be measuring the air in the interstitial cavity, right? Inside the wall cavity, or the air coming out of your system that's drawing air out from underneath a flooring material, for example, right? That's the air that I would measure in that case. So what is that comparison? How do these 2 compare to one another? And if the air that is in contact with the wet surface is substantially higher than the air above it, then we don't have enough airflow. Document it. Increase the airflow. Increase the speed of the movement across that surface, and then measure again. If the 2 are now comparable, it was a great adjustment. You will now have a faster drying rate, right? If that adjustment didn't correct the problem, continue to adjust, right? Now, that measurement is in contrast to another measurement that we discussed last month. And that was the measurement of something called ERH. And measurement of ERH is for a different purpose. It's an entirely different purpose, but it can still be used to understand if you're balancing your system. But in this case, ERH is used to understand if you're balancing humidity and temperature properly, right? Not airflow. So on the left-hand side, if you want to understand your air movers are working properly, leave them running, leave them on, and measure that humidity near the surface. Compare that to the humidity well above the surface. If they agree with one another, air movement's doing its job. If they don't agree with one another, air movement installation has failed, right? We need to make adjustments to air movement. On the right-hand side of the slide, let's talk now about assessing whether or not we have appropriate humidities and temperatures for our drying environment. And again, that's using ERH. Now, ERH stands for equilibrium relative humidity. That's what ERH stands for, equilibrium relative humidity. And instead of comparing our temperatures and humidities during the drying process, we're going to contain the hygrometer to the surface. With that containment, we can then allow that air to acclimate to the surface and understand what's happening with humidity and temperature in the environment. So let's dig into that a little bit deeper. We discussed this measurement a bit in episode 2. I want to dig a bit deeper into this measurement today and help you understand in more infinite detail how to perform this measurement. So first step is we begin by simply placing the hygrometer in contact with the surface. I would advise against putting the probe itself directly on a wet material because those probes are kind of sensitive to actually getting wet and that causing some damage. So just like you see in the image here, have a little bit of a gap between the sensor and the material. Then cover the hygrometer, right? Covering the hygrometer is going to be done with an impermeable material, like a clear plastic, like a 6 mil poly sheet, right? Once the sheet has covered the material, I'm either going to tape the edges if I'm on a vertical surface, or I'm just going to weight the edges if I'm on a horizontal surface, or you can tape them, right? Once that's taped down, then we're going to allow these to acclimate. Now, the acclimation is going to take some time. The amount of time required for the acclimation will depend on how wet the material is, how permeable the surface is, and how much temperature there is. The more energy there is, the faster the acclimation is going to be. Then we're just going to watch what happens. Now, when I say watch what happens, I don't mean stand over the hygrometer and just watch the hygrometer. What I mean is place it in this installation and then note the temperature and humidity that is displayed on the meter, and then walk away for 5 minutes and do something else. All right. In order to not impact your workflow in the inspection process, I would advise that you take this step right away, place the hygrometer there, and then go do something else for the next 5 minutes, then come back and check it. At a 5-minute interval, note the difference first in relative humidity, because that's probably the one that's going to take the longest. In this example, we placed the hygrometer originally, it said 55% RH, right? We walked away for 5 minutes, we came back, it now says 72% RH. It hasn't fully acclimated until you get 2 readings that match. So we walk away for 5 minutes, we come back, and we see a 78% relative humidity. Okay, again, hasn't acclimated. Go do something else and come back. We see an 80%. It's getting close, right? The relative humidities are only changing, just by a couple of percentage points. At that point, it's close enough that you could probably begin your analysis. But if you want to be really, really particular, come back in another 5 minutes and verify that the 80% hasn't changed, right? Now, when do you do this? How often do you do this? Is it practical to do this on every surface of every material on a mitigation project? No, right? Typically, this type of measurement to understand whether or not you have an appropriate humidity and appropriate temperature for drying, which is the next step we're going to get to here, is going to be done for materials that are low evaporation, they're slow drying, they're high value. You're on a project where you're getting immense pressure for the amount of drying time that you're going to spend because it's a retail setting. There's occupancy issues. They want to get back in the space. So this is a measurement that you're going to use when it's necessary to truly understand what your drying rate is going to be in the next 24 hours. And you want to know whether or not temperature and humidity need to be adjusted now in order to get ample progress in the next 24 hours. Not something you always have to decide. The previous measurement that we talked about and the airflow to ensure that airflow is balanced is a very rapid measurement. And I would advise that you do that measurement on any mitigation project because it's very quick and it's going to have a dramatic impact on your drying results. This one we're discussing now, it's going to be a more advanced tool you're going to pull out when you really need it. So once I have that data, what do I do with it, right? What does that information mean to me? And how do I transcribe that into mitigation drying decisions? To understand that, we've got to go back to one of my favorite tools, the psychometric chart. Okay. I know this is sometimes when you look at this chart, it may give you a headache, make you go cross-eyed when you look at this, but I guarantee you, and I know I've urged anybody who's been in the previous 2 episodes, look at a psychometric chart daily. All right. Put one at your desk, put one in your inspection kit, put one at home. Just look at it at least once a day for a couple of minutes and think like a psychometric chart. If you want to be a drying Godzilla, right, and this is a career for you in this industry, you want to be able to look at a psychometric chart and have it look to you like native language, right? Not a foreign language, okay? And the only way you're going to do that is by looking at it regularly. So in every one of these episodes that we have in Technically Speaking, somewhere I'm going to sneak in a psychometric chart. So with that, how do I use that information? I just got done placing the hygrometer on the surface. We measured temperature, we measured humidity, we let it acclimate. So what do I do with that, Brandon? What does that mean to me? So here's what we do with it. First of all, the measurements that you just took are the psychometric measurements of the material. So we're going to plot those measurements on a psychometric chart. In order to do anything with them, I need to translate that into more meaningful numbers. So let's say that our hygrometer, once it acclimated, got a temperature of 50 degrees and a relative humidity of approximately 50%. So 50 degrees, 50% relative humidity. Where those 2 lines cross on a psychometric chart, we go straight across horizontally, and all the way on the right-hand side, we get these psychometric values that we're going to use to analyze whether or not we have an appropriate humidity and temperature. Notice here that we have a vapor pressure of 0.18 inches of mercury. Okay, that 0.18 inches, what does that mean? What that means is that's the partial pressure of the water vapor and how that water vapor is trying to press out of the material. That's the force behind it. Okay, it will only leave the material if the opposing water vapor has less force. If water vapor is pushing into the material with more force, we're not going to see any significant drying, if any at all. All right. So to know whether or not that's appropriate, we need to then use the reading you normally take of your air, right? What is that normal temperature and humidity you took just standing in the middle of the room? Well, let's plot that. Let's say that that was 80 degrees Fahrenheit at 40% relative humidity. The air has a vapor pressure of 0.42 inches. Think about that for a second. All right, I know that it starts to get a little muddy once we get this many numbers on the slide, but think about that for a second. In the material, the water has a pressure of 0.18 inches of mercury. That's how bad it wants to come out. The air you're using to dry it has a pressure of 0.42 inches of mercury. The air is wetter. The air has more pressure. In other words, water vapor is traveling into the material. That's not conducive to drying. If anything, this material is going to gain moisture in the next 24 hours. So if this is a high value material, a complex assembly, a project where you're getting pressure, to get drying rates that are performing right now, this is immensely valuable, right? In a typical drying environment where you don't take this measurement, here's what would normally happen. You would take just your normal atmospheric readings. You'd say, oh, I've got 80 degrees and 40% humidity. That's not bad, right? Let's come back in 24 hours and cross our fingers and see if it works, right? You would come back to this job 24 hours later and you'd notice that material did not dry. In fact, you may even see a couple points higher in your moisture content and say, okay, well, that didn't work. It took you 24 hours to realize in that case that it didn't work. This measurement would tell you it's not going to work right now, okay? And it's much better in those circumstances where there is higher risk, where there is higher return on the value of restoration, where you have higher exposure based on the client. Whatever it is, this will tell you right now that an adjustment is necessary. So the last question in the conversation is, what adjustment is necessary? Okay, great. You told me there's a problem. And as somebody that I love in the industry used to always tell me, don't point out problems, give me solutions. Anybody can point out a problem, right? I know lots of people that are great at it, but give me a solution. So what's the solution? In order to understand the solution to this problem, what you have to understand is this: the relative humidity measured by that hygrometer that was contained to the surface of that material, that relative humidity is dictated by the amount of moisture in that material, how wet it is. And it wouldn't matter what the surrounding temperatures were. that humidity will remain the same as long as the amount of moisture in that material remains the same. In other words, I could make the material warmer. It's still going to give me a 50% relative humidity. I can make the material colder. It's still going to give me a 50% relative humidity. The reason it's giving me a 50% relative humidity is because that material is at an approximation of half of its saturation point. And that's just what the material is going to give you, right? So on a psychrometric chart, let's take that understanding, and I'm going to really highlight that 50% relative humidity line. Notice it's nice and bright now, okay? We started at 50 degrees for the material at a 50% relative humidity. Notice what happens when I make the material warmer. Raise the material to 90 degrees, 50% relative humidity remains the same. And take a look at what happens to the vapor pressure of that material. By raising the temperature of that material, I can see that I increase its vapor pressure. And now the vapor pressure of the water in the material is 0.71 inches of mercury. The air is only 0.42. Which way will the water travel now? Okay. Now I know for a fact that drying is going to occur, right? It's measured, it's absolute, right? I know for a fact it's going to occur. The only thing that could impede that fact is the permeance of the material at that point, right? If there is zero permeance, then the water is going to remain trapped. But if there's any permeability whatsoever, that water vapor is going to move. I want to pause on this for a second and kind of talk through this, and also remind everybody that the Q&A is open for questions. So make sure as I'm going through this, if I say a concept or a term or an acronym and I forget to define it, or you have a question about a specific application, drop it into the Q&A, because when we conclude the presentation today, I'm going to go through every one of those questions in the Q&A. So make sure you drop them in there. The second thing I want to point out while we're on this slide is that if you practice this type of measurement, here are all the things that you'll be able to do. First of all, I adjusted the temperature of the material to determine whether or not raising that material temperature is going to be adequate. Let's make that practical for a second. Let's say that you look at this 50 degrees and 50% relative humidity and you say, okay, this isn't enough. I need to warm up the material, right? So what would normally happen at that point is you'd make an adjustment to make the material warmer, whether it's raising the air temperature in the building, maybe it's a subfloor and there's a crawl space underneath. So you raise the temperature of air in the crawl space, that makes the subfloor warmer. Or maybe it's a wall cavity and you move to using an injection system to inject some warm air into the wall cavity, right? You make those adjustments and then you remeasure. And maybe it's just a laser thermometer that you're remeasuring with to get a quick, immediate temperature, and just shoot a temperature and say, okay, now the wall's at 90. So now you go back to the chart and you ask, is 90 enough? We plotted 90 on the chart. We see that our vapor pressure of the material is now above the air. Yes, it was. So that's kind of the practical way and process that you would apply that. The other way we could change this is, instead of making the material warmer, if that's not practical, the other side of the equation was, the air was wetter than the material, right? It had 0.42 inches, the material had 0.18. So instead of adjusting the material temperature, the other thing I could have done is I could have lowered the air's vapor pressure, right? I could have made the air in the environment drier. So that would be the other angle you could take. If it's not practical to make a material warmer, then let's focus on making the air drier. And what resources do I need to make that air drier? In that case, with this specialty material that needed such a low vapor pressure, maybe I'm using the wrong dehumidification technology, right? Maybe I should be focusing on using a desiccant in that application, or containing a desiccant directly to that material to get drier air immediately on the surface. And this measurement, again, would justify that decision, right? Sometimes desiccants, for those that aren't real familiar, desiccants can be relatively expensive pieces of equipment to run on a project. And sometimes justifying bringing in a piece of equipment like that can be difficult. But with documentation like this, it makes it a lot easier, right? A lot easier. Why was the desiccant used? Well, the desiccant was used because I needed an air vapor pressure less than 0.18 inches of mercury. That's pretty low, right? And my low grain refrigerant dehumidifiers weren't getting us there. So we switched to a desiccant, and then 24 hours later, we had drying progress, right? Really easy for me to tell that story and the reason why those adjustments were made. But again, it all comes back to using this psychrometric chart. Okay, so I'm going to close this conversation out with just one more call to action on the psych chart. The only way you're going to get to that point where you can make those types of arguments and make that kind of conclusion definitively is to get comfortable with these charts. And there's so many applications out there where the grains get calculated for you, or the psychrometric chart doesn't get used because things are being done in the background on the meter, but it really removes the solid practice of being comfortable with this chart and kind of that old school methodology of thinking in terms of psychrometry. And an app or a meter that translates for you isn't going to get you to think in terms of psychrometry. Only a chart will. So practice it on the chart. Even if your daily documentation isn't using a chart, just take a job record from that day and just practice a couple of measurements on the chart and ask yourself a few questions about, did I really make all the decisions I could have made? And am I really justifying all those decisions appropriately using a chart? And you'll be amazed how quickly you start to pick that up and think in terms of psychrometry. Okay. All right. So with all of that said, let's go ahead and get into reviewing some of the industry secrets that I wanted to touch on today. Just as, again, a quick note, we're going to get into the Q&A session here in just a moment. So if you haven't had a chance yet to drop your questions into the Q&A, please do that now. So a couple quick items in review. First of all, in terms of balancing a drying system, the most important principle is to ensure we understand that we measure twice, right? I measure at the floor or at the wet surface and in the air above it. I measure yesterday, I measure to today. We make comparisons between two measurements. One of the largest stumbling blocks that I see with psychrometrics with many restorers is when they're first trying to understand how to apply psychrometry, they'll take a measurement and then expect that measurement to tell them something, right? And it doesn't by itself. It doesn't matter what we're measuring, anything in life or business for that matter. In order for the measurement to mean anything, I need a point of comparison, something to compare it to. Compare the floor to the air above it. Compare yesterday to today, right? Compare vapor pressure of air to vapor pressure of material. It's all about comparisons. It's the difference that tells me what actions I need to take, right? It's the difference. So measure twice. The second principle I really wanted to highlight today is this measurement of equilibrium relative humidity. It's not something you're going to use all the time. Containing that hygrometer to a surface, it takes time, it takes acclimation, but when you're dealing with high value materials, high sensitivity materials, complex materials, you're dealing with a project where there's a high sense of urgency on your drying times for whatever reason, then ERH can become a very useful tool. My suggestion to you is to come at that project with more than one hygrometer if you're going to do it, right? A high value material, a high value project is going to afford the use of more than one inspection kit. So use more than one hygrometer so that you can leave a hygrometer to acclimate on a surface and leave a hygrometer to acclimate on a surface while you do other things, right? While you take other activities into play. You're not going to want to just stare at that hygrometer as it acclimates. It'll be like watching paint dry. Okay, but it can be very useful for understanding that vapor pressure and that role that vapor pressure is playing. Again, that's very different than measuring the balance of your air movement in the environment. When we're trying to understand how effective our air movers are creating circulation, no containment, right? You're measuring the effect of humidity with air movement in play. Really important to stress that. And then the final concept I wanted to really hit on hard today is the importance of using the psychrometric chart, right? You should be looking at a psychrometric chart regularly in this industry if you have any impact on the decisions that are being made on drying projects. You've got to think in terms of psychrometry. And that's what a psychrometric chart is, right? It's an expression in a graphical format of the relationship between temperature and humidities and vapor pressures and dew points. It expresses that relationship. And the more you look at a psychrometric chart and think about those readings, the more your brain is literally going to think in terms of psychrometry. And the closer you're going to get to drying Godzillaism, right? Is one of my favorite phrases. So with that, folks, those are the primary concepts I want to touch on today. Before we get into the Q&A session, real quickly, just want to highlight where we're going next. Again, just to kind of recap, my name is Brandon Burton, CoreLogic and NextGear, and also the chair of the ANSI and ICRC standards. And I am going to host several episodes of this series moving forward. Today's episode was balancing the drying environment, but coming up next in episode 4, we're going to talk specifically about maximizing airflow resources. And that's going to be on April 26th at 10 a.m. Pacific, 12 Central. So go ahead and mark your calendars, make sure you've got that time blocked out, because you can only attend the Q&A session that we're about ready to go into when you're here live. When we finish up the recording and post the recording, it's going to cut right after my commercial for the next episode, right? You're not going to be able to see the Q&A session. So make sure you attend that live if you want to get the full value out of the presentation. Just so everybody knows, in episode 4 with maximizing airflow resources, We're going to dig into a couple things there. First, I'm going to get really deep into the S500, the standard, and talk about how to deploy the air mover calculations that are in the standard. And then we're going to draw on some of what we learned today and talk about the balancing act of moving forward with that air mover installation and how we adjust that air mover installation. We're then going to go into inter-air drying systems and start talking about cavity drying and hardwood floor drying and other places where inter-air drying systems are deployed and how to deploy them and monitor them. So it's going to be a pretty jam-packed episode. I'm going to talk a lot about air movement in virtually every way that air movers need to be understood. I want to thank you again for your time today and remind you that my email address is down here on the bottom of the presentation, brburton@corelogic.com. Do not hesitate to reach out if you'd like to talk psychrometry, drying, industry standards, or even how to get your CECs. I'm here for you, and stay in contact. Thank you very much for your time, and we'll see you in April for episode 4.